Right, and so I've broken this session into four topics really. The first is just why we're measuring the atmosphere. What's the value of measuring the atmosphere? Well, I'm also going to look at the structure of the atmosphere. It's important that you all have an awareness, even if you're interested in looking at the surface. It's quite important that you understand what the atmosphere is like, partly because it's good to know what you're looking through to look through to the Earth's surface. The work that you will do with people like Caroline Nichol, who's interested in looking at the surface and using hyper and multispectral imagery, she has to take into account the atmosphere because it gets in the way and you want to get rid of it. And it's also worthwhile understanding the structure of the atmosphere so that you can engage and read in topics related to the Earth system and climate change. And also just having an awareness of, I'll show you a graphic, for example, that indicates just how high the Earth observation satellites are. And I know you've had one slide that shows you the relative height of low Earth orbit satellites compared to satellites in geostationary or geosynchronous orbit. I'll show you another one that's got a little bit more detail perhaps on the scale, just to give you a sense of what we're dealing with here. Then I'm going to look at radiation in gases. If you did degrees in physics and astrophysics before you came here, or if you did my undergraduate option, or if you did something else that was looking at how radiation passed through gases, some of that will be revision rather than new. But I'm guessing that for many of you, this will be the first time you'll have thought about how radiation passes through gases. And we will, I'll talk you through that. And that should hopefully lead directly to you understanding the different observation scenarios, how we measure the atmosphere and how that's related. Right, so why measure the atmosphere? I'm going to go through some basically nice pictures and video, the kinds of things that we measure in the atmosphere. The key thing is it's a significant part of the Earth system. One of the, if you arrived at Earth from a distant galaxy or a distant solar system, and if you arrived at this solar system for the first time and you were observing Earth, the very noticeable thing that you would see is that it's covered in cloud. So the difference between a cloud-free and a cloudy Earth atmosphere is quite significant. So clouds are really important. I'm not actually going to talk a lot about how you measure clouds. For the most part, once you can separate the difference between clouds and snow and ice, because you'll notice, for example, over Greenland, you can't see where the clouds are because the clouds are very difficult to see in the visible part of the spectrum if you've got snow in the background. But there are techniques to differentiate them. And just observing the processes of clouds is quite significant. We'll also talk about a little bit about how clouds form. And at the end, I will mention a little bit more about what's called the Earth radiation budget. So that's how much energy is arriving at the Earth versus how much is going. And it's quite a significant difference if you look at a cloud-free Earth. The amount of energy that would absorb is about twice as much as if covered in cloud, because you've about a third of all the radiation that arrives from the sun is immediately scattered back out into space as a consequence of the cloud cover. Cloud cover, of course, when you're trying to look at the surface, that's what you want to see because you're not interested in the clouds. There are some parts of the world, especially in Western Africa, for example, that even though instruments like the Landsat satellite have been in orbit since 1972, they still haven't managed to find some cloud-free pixels in some of these areas in West Africa, and there's a few in other parts of the world just because of constant cloud cover. For those of you new to Edinburgh, you'll be surprised to know that Edinburgh is not in that bracket, is that you do actually get some cloud-free days. And that is, and nowadays with satellites that can give you a much higher repeat coverage so that you can come back more often, is now the case that I think there is nowhere left that hasn't been measured by satellite. So even in the cloudiest places in the world, you do occasionally get some gaps. And if you can accumulate them enough, you can create these very large scale, global scale cloud-free mosaics. If you follow the news in the Earth observation community, you'll see that Planet, for example, is just about to release, well, it's being funded by the Norwegians, but the entire tropical region, so plus and minus 20 degrees in latitude, they're going to generate a 6-month mosaic every year for, I think, the last 4 years and the next years, in order to aid deforestation mapping. But we were interested in the atmosphere, and the atmosphere is dynamic. So this Meteosat, a little video just to show you the fact that the clouds don't stay still. You can monitor the location of clouds, and that will give you some information about the wind speeds. And one of the key things about the dynamics of the atmosphere is that you'll notice that most of the clouds around the equator are traveling to the west. Most of the clouds at the higher latitudes are traveling towards the east. And that's part of the dynamics of the Hadley cells and the Earth circulation. And we can monitor that through satellites, where these are all I've shown you so far have been in the visible. But we don't always have to be tied to the visible. Sorry, swirling beach ball of doom while this goes on to the next slide. One of the challenges of putting in nice videos and everything to entertain you is that it does make these files very large. So here's another one that's just a close-up over Northern Europe, and this kind of information is used now as standard into weather forecasting models. One of the key distinctions you'll hear in the literature is to do with whether a satellite is essentially a research satellite or an operational satellite. Operational has a very specific and important meaning in Earth observation. It means that it is the data that it is providing is now so important that there is a replacement satellite ready to go whenever anything goes wrong. So the weather satellites, for example, are all operational. So they're not run by ESA in Europe, they're run by EUMETSAT. And in the US, for example, they're run by NOAA rather than NASA. And that's because they are now so important in the weather forecasting that if anything goes wrong, they immediately replace them. So there's a continuity of data. But we can also look in different parts of the spectrum. So once we go into the infrared and the thermal infrared, we start to look at specific wavelengths that see the water vapor very specifically. And here you can see the variations. The density of the water vapor is often related here to the height of the cloud. So we at the equatorial region, where these very high convective clouds are forming, there's a significant amount of water vapor in the atmosphere. And you can see at the higher latitudes all the dynamics of the cyclones and anticyclones as the Earth moves around. And you can see there's quite significant horizontal variation in properties like water vapor. And that's an animation. So that's a composite of all the geosynchronous meteorological satellites. And you go notice that band right across the equator. That is the what's called the intertropical convergence zone. So hopefully very quickly you can see from a meteorological point of view, this kind of information is vital. The meteorological satellites are providing information from geosynchronous orbit every 15 minutes. The low Earth orbit meteorological satellites every 2 or 3 times a day. And again, my poor old laptop is thinking while I try to get onto the next slide. So I'm going to talk you through a little bit about the dynamics of the atmosphere. Just to put that into context. You know what, I'll have a quick search to see if this doesn't look like there's any hands up. I don't have many of these videos, so hopefully it will speed up a bit in a minute.
Hello, Ian. I don't seem to see the video actually moving.
At the moment, it's not moving because I've got this swirling beach ball of doom, which makes sense to anybody who's got a Mac. So it's trying to move on to the next slide.
Okay, so I'm not missing anything then.
You're
okay.
not. It's just so it's just a moment for everybody to reflect.
Okay, thank you.
The good news for me is that I'll be able to use this as justification for why the school needs to get me a new laptop. Oh yeah, and somebody's asking, so the slides, yeah, the slides are ready to go. I'm going to put them up onto Learn as soon as we're finished. They won't have the videos in them. I should be able to find a way to upload the videos. I'll have a think about that. But one of the best resources to go to is what's called the Goddard Data Visualization Studio, and I'll just type that in. So if any of you are ever doing any presentations or lectures at some point in the future, I recommend this as a great source. And it's the NASA Goddard. So NASA Goddard is one of the key NASA centers. Oh yeah, that's a good question by Seamus. This it's just reflected, I think, in the actually, let me just quickly check. No, I suspect what it is it's emission. It'll be in the water vapor band in one of the longer wavelengths. Right, I'm trying an alternative. I don't know why it is particularly upset about the next slide. But hold on. Right, we got there eventually. So the key thing, I wanted to show this slide because it is it's taken from the low Earth orbit. So the previous slides that I showed were from the geosynchronous satellites, so at 36,000 kilometers away. This is from a low Earth orbit, so nearer 700-800 kilometers. And this kind of high resolution imagery is collected at least twice a day everywhere in the world, and it is used to directly monitor the processes. This is a visible image, though. This is what you would see if you were on the International Space Station looking down. What I want to talk about today is beyond that, because mostly in the visible part of the spectrum, you don't see much of the atmosphere. You see through it. And so we're going to look at how do you actually detect concentrations of things like carbon dioxide. Oh, was that a question there, or was that just somebody who forgot to turn their mic on?
You're not screen sharing again yet.
Ah.
Together.
Thank you for pointing that out. I ended the screen share in order to try to save the. Okay, so you should now be seeing this high resolution low Earth orbit image of a big hurricane. It's not a hurricane by that time, but it's in the North Atlantic. I don't hear anybody complaining, so I assume that we're back on. But what I'm going to talk about more today is how you measure some of the actual chemical constituents or the physical properties such as pressure and temperature. And you'll notice that this is measurements from NASA's Orbiting Carbon Observatory, and it's measuring variations in carbon dioxide concentrations. But the thing I wanted to stress here is that it's showing it on a scale of parts per million. So this is parts per million, which is the equivalent of counting how many people are participating in this online lecture out of the entire population of Scotland. And so the concentrations that we're looking at are very, very small. It's quite incredible that we can make these measurements. We can actually even also make measurements. One of the techniques I'll show you later is so sensitive it can pick up concentrations of gases that are in parts per billion, which is like counting how many people are in this class out of the entire population of the world. And so that's the level of concentration that some of these gases are in, and we're still going to be able to detect them. Here was a topical one that you might have seen some of this that came into the press. This is looking at nitrogen dioxide, an industrial pollutant, and you'll see the difference between January and February here in terms of the concentrations. And as there was some discussion, if some of you followed that earlier in the year, there was some discussion that pointed out that, well, in February, that's the Chinese New Year. So of course, the pollution is much less. But there's been some nice studies looking at cities like Wuhan that show that, well, that you always get a dip in the nitrogen dioxide during the Chinese New Year, but it usually rises again later into February, and that didn't happen. And so what was being discussed is whether or not the measurements of the atmospheric constituents were an indication of changes in the habits of the population in terms of the reduction in driving. So the restrictions in due to COVID were meaning that just far fewer people were driving. A lot of the industries were slowing down and not producing quite as much nitrogen dioxide. So there's quite a lot of things that you can do in that social context. This one here is measurements of total ozone. So it's comparing it from 1979, 1987, 2006, and 2011. And so the low concentrations over the Antarctic, this is what is famously referred to as the ozone hole. And you'll notice that it doesn't actually look, by 2011, it doesn't actually look like it's very much different from 1987, but based on all the models. So about 1979 was when they introduced the Montreal Protocol to try to reduce the pollutants that were destroying the ozone. So you can see that there was definitely a reduction in ozone from 79 to 87 while the Montreal Protocol was starting to get implemented. And the studies would suggest that we've managed to stop it from getting worse, and it has supposedly got a little bit better in the last few years. But the studies and our understanding of ozone is almost entirely driven by satellite measurements of the stratosphere. Now that's not quite strictly true in terms of the history of ozone, because the first measurements that actually showed the formation of the ozone hole were British Antarctic Survey measurements made from the ground. But in terms of our understanding of the dynamics and the chemistry, that has been primarily driven by measurements from space. Now, another interesting feature of the atmosphere is that it's full of aerosols. Anybody who suffers from hay fever knows that at least of the existence of one aerosol, which is the pollen in the air. And get blown around quite considerably and up into the 2 or 3 kilometers up into the atmosphere. But as well as pollen, there's lots of other aerosols that end up. So these are actual particles. So Saharan dust, for example, gets blown up by big sandstorms and can get blown across the Atlantic, and is actually one of the major fertilizers of the Amazon basin, is the nutrients that get blown and picked up by the wind in North Africa and blown across the Atlantic. And we can actually measure these dust columns. Very occasionally, dust will actually get caught up into the air that's getting driven. You can just about see some of the colors up into the Northern Europe there. So there's definitely been cases of Saharan dust ending up landing in Scotland. And this is more recent. This is some of the smoke plumes from California, and just showing that by detecting these aerosols, so smoke and black carbon, so soot is another aerosol, and it can get picked up and taken right across the continent and into the North Atlantic. And soot is quite important because it's a form of carbon, and it will eventually get rained out into the surface. If it lands on surfaces like glaciers or ice sheets, it actually aids in their melting because it makes them slightly darker, and therefore they absorb more of the incoming solar radiation. I just listed here the kinds of aerosols that you get in the atmosphere, and all of these aren't necessarily measurable from space, but many of them are. So I've grouped them into 3 different things. The first one is what are called hydrometeors. So hydrometeors are anything that is made of water. So fog and mist and raindrops and ice particles, they're all hydrometeors. And clouds. So if you look out, in fact, from my window, it's a good day to look out and see a nice blue sky and white clouds. Now, very quick show of hands. Let's see if I can do this just to get you engaged. I think you can put up your hands, but put up your hands if you think. So I'm going to give you 2 choices. Okay, so if you think clouds are made of water vapor, put up your hand now. Oh, hands going up. That's nice. Good stuff. Few more hands. Now, some of those hands might go up again when I give you the second choice. The second choice is that clouds are made of liquid water. So take your hand down if you're sticking with your vapor. And liquid water, is that all the hands I'm getting for liquid water? Ah, that's interesting. So some of you might get pernickety here because you're the very colloquial term for vapor is arguably small droplets, but in a meteorological context, when we talk about water vapor, we're actually referring to the water in its gaseous state, so water gas. And so that's different. That's different from liquid water droplets. And the clouds that you see in the sky today are actually droplets of liquid water. They're very small. They're typically, in 1 to 100 microns in size, but they're made of liquid water, and that's going to be significant when we look at scattering later on. And that's one of the little experiments that we're going to do with the milk and the water and the light. Water vapor in a proper meteorological context. Just checking the chat in case anybody's disagreeing with me there. Oh, somebody's asking how you raise your hand. Now, one of the things that I've seen before is that what I have as my interface on as the host can be different from your interface. Yeah, thank you, Seamus, for answering that question as a participant, because you'll see difference. So if you don't know how to raise your hand, check the chat. Seamus has helpfully given a bit of advice on how to find the raising your hand. So water vapor. So this is going to be our experiment in a second. We're going to go down this list, and I'm going to talk about clouds in a second, because how do clouds actually form is going to be one of my questions. One of the reasons that is what's called cloud condensation nuclei, and that's right down at here. So it's a generic expression for lots of other things that are cloud condensation nuclei. But the natural aerosols that occur, soil dust, sea salt, so just the spray and the dynamics of the ocean surface sends little droplets of seawater into the atmosphere. They're small enough to be suspended by the air long enough to then actually dry out, and they just leaves the salt, and that actually becomes small particles that are suspended in the air. Volcanic dust. So volcanic dust is little shards of rock and glass, a very significant problem for the airlines. So some of you may remember when the volcano in Iceland and the European to North American flights were all disrupted by that. So I got disrupted by that one point and ended up in a queue at Newark Airport, and I had to wait for 4 hours to get my connecting flight, and that was no fun. So I definitely remember the impacts of volcanic dust. Biological debris, including pollen and other volatile organic compounds these are all naturally occurring and happen all the time. But we have added to that as human beings in terms of industrial particulates. Soot and black carbon occur naturally as well. So fires occur naturally around the world. Smog is a portmanteau word. It's the combination of fog and smoke. So when this soot actually combines with the small particles of fog, it makes a very nasty concoction, which is easy to breathe in and very bad for your health. But I want to talk about the cloud condensation nuclei. Okay, so this is our first home experiment. So what's time? Not quite time for a break. I'm gonna show you this experiment, and then I'm gonna get you to have fun. If you want to join me in this experiment, I'm going to give you about a minute to go and get. This is where you need. Hang on, I'm going to come out of the screen sharing. And come out of the slides. So you need one glass, something fizzy, and something. I've got sugar, but it can be sugar or salt or anything like that. Oh, I didn't say that on the list, did I? Right, I'm going to give you a minute, and if anybody wants to go and try this experiment at home, because I know you're all at home, I'll give you a minute to go and get that. And put a hand up if you're going to join me in this experiment. So if nobody puts their hand up, I'll know I can just cry. But if there's anybody who actually wants to try this, all right, Kerry's going to try it. Good stuff. Also, you can use this same technique in order to annoy your friends when you eventually get to go to the pub again.
Can I just ask a quick question?
You can.
Does this process also apply to fog, or is that unrelated? So
fog, mist are all types of clouds. They're all small droplets of water. It just the size of them is what makes the difference in terms of meteorologically.
Awesome, thanks.
But my question, what I'm going to show you now, and Kerry, I think, so Kerry, when you're ready, if you've got your salt and a glass and something fizzy, when you're ready, you can if you're really brave, you can put your camera on, you can show everybody else you're doing the experiment. Or
is sugar okay?
Sugar is perfect. I've got sugar.
I have to.
Right, so I'm going to open. So what I want to show you is is the formation of what cloud condensation nuclei do in the atmosphere. If you have nothing, hang on, let me just pour this. Now I'll tell you, what fizzy thing have you got, Kerry?
I've got Coke.
Okay, now Coke. The reason I chose cider, I've got Coke in the house as well, but the reason I chose cider is because you can see into it a little bit better, right? I've also cheated. I'll tell you what's happening here. This is a liquid that's got carbon dioxide sort of saturated in it, okay? And the carbon dioxide makes the bubbles. Now, the bubbles can't form on their own. Now Kerry, I didn't tell Kerry this trick, right? But that's always how, you know, a performer doing any trick will always tell you how to do some of it, but not all of it. Oh, Ewan's got his hand up. Is that a question, or are you doing the experiment as well, Ewan?
I was trying to do the experiment as well.
Okay. Are you going to share? Are you going to turn on and share your activity? Kerry's been very brave, so. Right. So I've actually cheated here. I've lined the inside of this glass with oil. I got a napkin and some olive oil, and I wiped the inside of the glass. And the reason for that is that an old glass or anything that's got any kind of dust or anything on it will actually form an object that allows the carbon dioxide to come out of the liquid, right? And so what you need in order to get the carbon dioxide out of this liquid is that it needs somewhere to condense onto. It needs nothing. If there's no sharp edge, if there's nothing that actually allows it to form, there'll be almost no bubbles that would form in this. And it's too long to do that before and after. But I did this in this glass, and it's quite an old glass. And so I think it's got lots of little tiny scratches and everything inside the glass. So when I poured the cider into it, it made an annoying head and actually generated many more bubbles. Than you'll see a few bubbles in there, but it had quite a lot more bubbles. And so the way to cheat with that is that you basically give it a oh, Manchen's got it as well. You basically wipe some oil in it, and the oil covers all those edges, and it keeps the liquid away from the sharp edges. So I've got a nice headless glass of fizzy stuff. Let me put a light on it just to so you can see it. And what I'm going to do is I'm going to take a little bit of sugar. I've got sugar here. I'm going to put it into the glass. And because these little grains have got lots of nice sharp edges, the carbon dioxide is going to be able to form on it. And all of these bubbles will generate and will basically create some clouds. So you see, it's not just those parts continue to generate lots of bubbles. And if I put some more in, yeah, it's really going crazy now. All that carbon dioxide suddenly coming out. It wasn't doing that before, and it was only because it's not because of it, it's because of the fact that you're generating lots of tiny little edges that creates allows the carbon dioxide to actually come out of because the carbon dioxide is saturated in there. It wants to come out of the liquid, but it can't do that spontaneously. It needs something to set that off. And I'll put some more in. And it's not only fun to watch and very mesmerizing, but it's basically demonstrating what cloud condensation nuclei. So all of those aerosols in the atmosphere is what form the clouds. If you have a perfectly clear atmosphere with nothing in it, clouds wouldn't form because the water vapor in the so the water gas in the atmosphere wouldn't be able to form into the little droplets that form the clouds. So you need these cloud condensation nuclei in order to actually allow the droplets to form, to condense on these aerosols, and that's what creates clouds. So the entire Earth system, because clouds are very important, are driven by these aerosols in terms of what their contribution is and how they form the clouds. Now, the trick that you can play on your friends is that you basically bet them that they wouldn't put like a very large spoonful of sugar or salt into their beer. And if they don't know this trick, I'm not going to do it, but you'll notice I've just beaten small amounts in. If you take a tablespoon of sugar and you pour it into a pint of beer, it will basically look like a volcano because it will just go whoosh, and all of the carbon dioxide will come out spontaneously and flow over the table and make a terrible mess, right? So don't do that at home. Do that in the pub when somebody else gets to clean up. All right, so that's cloud condensation nuclei. Did it work? Kerry, Ewan? Man, did you do it also? So that's yeah, that's how cloud condensation nuclei are. So that's how you can experiment with meteorology at home with fizzy drinks, and doesn't necessarily have to be beer or cider. Right, I'm gonna use that as an interlude. The next practical session we'll do later involves a glass. It's better if you've got a bigger glass. So if you can get a glass, that's all the better. And I'm going to get you to put a tiny little drop of milk into it. And then we're going to look at some of the scattering properties. And you might not be able to do it if you really want to be able to find somewhere dark. So a cupboard or underneath underneath your duvet or something. But we're going to do that later. But what I suggest is, not least of all, just for my voice, is that I'm going to suggest we take a little 10-minute comfort break. So it's, according to my clock, it's 6 minutes to the hour. So 5 past the hour, we'll reconvene. So everybody can go and you can either now go and do that experiment yourself now in the comfort of your own home, or go and get some water and milk and a torch. The torch, a light on a smartphone, for example, is good enough. A torch of any kind or a bright light will also work. And then in the second part, I'm going to talk about the structure of the atmosphere. Okay, if there's no, Kerry, you still got your hand up. Is that because you've got a question or because you just forgot to put your hand down?
I just forgot to put it down.
Great. Right, I'll go and check if there's any questions on the chat, and otherwise we'll reconvene in 10 minutes. Okay, everybody, time to get started again. Full marks for Seamus for getting onto LinkedIn already. Conveniently using the same picture for everything, which is also a handy way. Right, if everybody's back, if you look in the chat, you'll see a link. And if you go to that link, that's a link to my blog that has a visual on it for looking at the height of an Earth observation satellite. But it is also a good way of looking at some of the properties of the atmosphere in terms of the structure and the scale that we're talking about here. So what I'm going to do, I'm not going to assume that you can all access that SVG version. SVG is a scalable vector graphic. And so if I just share my screen. If you go into that link, so this one, you can follow this yourselves by just actually, you can watch the screen and you can see me doing it, or you can just go onto that link that I sent you and go onto the SVG version, and you can zoom in and roam around as much as you like. The key thing about the scalable vector graphic is that it's not a huge file by having a very large bitmap like a PNG or a JPEG. It actually keeps everything in vector information. And you should be learning the important differences between vector and raster images. But for example, if I quickly, you can zoom in, and I'm going to show you this just to start, is what it means being a scalable vector graphic, is that I can zoom right in. And like I say, you folks can do this at home. So I've tried to do everything in this graphic to scale. So that's the world's tallest tree. And certainly at the time I made this graphic, the world's tallest building was the Burj Khalifa in Dubai. it's quite possible that that has been surpassed by now. But that's just to give you an idea in terms of the scale that we're talking about of the largest tree to the largest building. And an indication of the cloud layers. So nimbostratus, cumulus gets higher, cirrus clouds way up the top. Let me just widen this. And then we can see further. Further, but cumulonimbus clouds by comparison are very large, and sometimes you will even see the top of the cumulonimbus clouds will actually start to flatten out in a classic anvil shape, and that's because it's actually reaching the temperature inversion at the top of the troposphere, and so it can't actually rise any further. Warm air stops rising once you get to that inversion. Hang on, I'm just going to reload that for a second. So if you're looking at this yourself, the other thing that you might like to note is that the brown area showing you the land, oh, sorry, the brown area showing you the land, that's the proportional area on the surface at that height. Whoops. That's the problem with scalable vector graphics, is you can lose it altogether. So what I mean by that is that if you look at the curve of the brown area, that's in proportion to the, let me try and do this properly. It's always nice doing live things, but it is prone to problems. So this brown area here, you'll see that it reaches up to the height of Everest, about 8.8 kilometers above sea level. Is that slope in the brown area as it comes down to the sea level, that's proportionally the tick mark. So that's the percentage it tells you at the bottom. Each tick mark is 10% of the Earth's surface. So that's 1, 2, 3. So about 30% of the Earth's surface is covered by land, and 70% is covered by water. And less than, what's that, about 5% of the land surface is higher than about 2 kilometers. So that's how you can read the shape of that graph at the bottom. And likewise, in terms of the depths of the ocean, getting down to the world's deepest point right down here, is that's in proportion to the area covered by that deepness. So it's only a couple of percent that gets down lower than, what's that, 8 meters. And the deepest point there, so the Challenger Deep, just a bit of history for you all, the Challenger Deep was named after was discovered and then named after the Challenger expedition, which was actually led by a professor from the University of Edinburgh in the 1880s, 1890s. So over 100 years ago. The Challenger expedition was, anybody who studied oceanography will have heard of the Challenger expedition because it's seen as the birth of modern oceanography, of actually going out and making physical measurements of the ocean. Anyway, we're going to look, it's this area here. So I should be able to scribble on here. This bit here is the troposphere. It's about roughly the first 15 kilometers of the atmosphere from the surface. That's about 90% of all of the mass of the atmosphere. And that is where all the weather happens. And that is pretty much where all human activity happens, apart from very high altitude aircraft that can get as high as 20 kilometers, typically historically developed by the military in order to do spying, because if you can fly at 20 kilometers, you can avoid being hit by surface to air missiles. Most aircraft, so if you've flown in a very high altitude aircraft, you've only gotten up to about 12, 13 kilometers. Radiosondes and balloons got up to as high as about 40 kilometers. Not always that high, but they send up little measurements. I shouldn't have to tell you that these pictures are all not to scale, but the things right down are to scale. Let me just clear that off. And if we scroll up, we get through into the stratosphere. So from about 15 up to about 55 kilometers. That's the stratosphere. That's where things like the ozone layer is very, very thin by now, but getting thinner. It drops off exponentially. Once you up into the mesosphere, it's still very thin, but it's not so thin that so meteor showers typically are happening up in the mesosphere. That's the small particles and dust-sized particles that are orbiting the sun just as the Earth is, and as the Earth goes through them. In fact, I think there's a meteor shower this week, so watch out for that. And these tiny specks of dust coming through the atmosphere, and there's still enough atmosphere up in the mesosphere that it's the burning up of these little particles that you see as meteors. If you're thinking of going up with Virgin Galactic into space, you're going to cross what's called the Karman Line, about 100 kilometers. And that's a fairly arbitrary line, but historically what they discovered when they were doing early rocketry was that once you get above 100 kilometers, orbital dynamics starts to take over rather than the aerodynamics of the atmosphere. So there's below 100 kilometers, there's still enough atmosphere to have to think about aerodynamics. Above 100 kilometers, it's mostly the orbital dynamics that takes over. The aurora is not much higher than that, but you have to keep going if you want to get into the first place that you're actually got. It's definitely thin enough to go into orbit. The space shuttle would go up to about 250, 300 kilometers in its heyday. So typically about 320. The space shuttle would only go into orbit for about a week or 10 days. And so it didn't matter that it was still enough atmosphere to slow it down. It wasn't trying to last for 2 or 3 years. Now you'll notice on the scalable vector graphic is that you can actually zoom in, and what I've done is that in these circles there is actually a little outline that represents the size of the space shuttle relative to on the same scale, the height and the objects on the surface at the bottom. So you can zoom in and actually see the height. And if you go a bit further up in the atmosphere, you can get to the International Space Station. And likewise, if you zoom into that, you'll see that there's just a little graphic that represents that's the International Space Station to scale. I haven't done that with the other satellites, but you have to go a bit further higher. So ISAT, Steve Hancock will talk to you about lidars and lidars in space. Lidar systems try to fly a little bit lower because they've got issues to do with power because they're firing a laser and they're trying to measure the reflection coming back. And if you go a bit higher, you get to things like the Sentinels, which are about 700 kilometers. So that's a fun little graphic. You can go and read the rest of it. It adds to that graphic you got last week to do with orbits. But the key thing for us looking at the atmosphere is that we are probably 700 kilometers or more away from the bulk of the atmosphere that we're trying to measure. And the atmosphere that we're trying to measure also is very dynamic, the things happening, and there's a land surface and water surface in the background when we're trying to measure the atmosphere. So I've got a couple of slides that will remind you of that. That's just the same graphic. That was just in case the scalable vector graphic wasn't working. And but go and have a look at the scalable vector graphic. There's lots of things to read in there. It will tell you information about the various structure bits of the atmosphere. And it will also remind you that you have to go considerably further, considerably higher to get to geosynchronous orbit. The Sentinels, yeah, about 700 kilometers. The sort of 1 and 2, 800 kilometers. That's about the limit. You won't get much higher than that for a Earth observation satellite. So the other thing to look at is in terms of the atmosphere. This graph on the right, we're going to look at a little bit more detail, just so you've got it related to that figure. It's about 0 to 100 kilometers that we're looking at. And that's our troposphere. That's where all the Earth weather system, climate is all happening in that little strip at the bottom. Now, the other thing I wanted to show you here is the temperature profile. Now, just to note here, two things. One is it's in Kelvin. And if you're not in the habit of using Kelvin, I recommend that you get into that habit now. Kelvin is a much better temperature scale because the zero actually has some physical significance. The Fahrenheit scale is based on, what's that based on? It's based on the temperature of the human body at 100, and I can't remember what the zero is in Fahrenheit. And this Celsius scale is based on the freezing point and boiling point of water at standard atmospheric temperature and pressure, or standard pressure. But Kelvin is a little bit more non-arbitrary, because it relates to the fact that once you get down to 0 Kelvin, there is no energy in the object that you're looking at. So in fact, there is nothing in the universe that we know of that is at 0 Kelvin. Even deep space is at 3.1 Kelvin. But so we're using Kelvin here. And the other thing to note is that the atmosphere drops off in density exponentially. But what we're measuring here is a thermodynamic temperature, not the temperature that you would feel if you got out of a balloon at 40 kilometers in altitude. It would feel extremely cold, but it would feel extremely cold not because of the average kinetic energy of the molecules, but because there's just not any molecules. So this graph is representing the temperature that you would get if you took that air up at 40 kilometers and brought it down to sea level. That what temperature would you measure from that? So it's more of an indication of how energetic the particles are in the atmosphere at that point. In the troposphere, it drops off with altitude fairly straightforwardly. What's happening here is that the Earth is being warmed up by the sunlight. The sunlight warms up the atmosphere above it by convection and conduction. It's moved through by convection. But as you get further and further away from the Earth's surface, it gets colder. It feels colder to you as you go up a mountain, but that's also to do with the density. But it's actually getting colder because the energy is being warmed by the Earth. And if you get further and further away from the Earth, you get colder. Into the stratosphere and the mesosphere, you actually, in the stratosphere, it's a temperature inversion. So if you remember, I said about the cumulonimbus clouds, as they reach the tropopause, it stops getting higher and it spreads out in this anvil shape. That's because of this temperature inversion. So warm air doesn't rise anymore in the stratosphere. And that the reason that you get this trend here is because roughly at 40 kilometers, this is where the ozone layer is absorbing all the ultraviolet light coming in from the sun, and it's warming up. So the ozone itself is warming up, and then it's bouncing about and knocking into all the other particles in the atmosphere and getting it warmer. So it's warmer here just because of the ozone layer, and then it cools off again as you get through to the mesosphere. So in terms of the terminology that I will use for the rest of the class, we have the troposphere, and then we call what we call the upper atmosphere. And the upper atmosphere is usually upwards from the troposphere. It's much thinner. It's very difficult to detect. But we'll see how we might be able to manage that. Now, just as an indicator of scale, on the scale of this view of the world, your troposphere is something like that, okay? Possibly even a little bit thinner. Okay, so the incredible thing, if you want to use another visualization of the scale of what we're talking about, if you take a football or a classroom globe and you put a piece of paper on the edge of it, the thickness of the paper is proportionally the thickness of the troposphere compared to the size of the Earth. So although I show those diagrams and it looks like there's lots of things going on in the troposphere, compared to the size of the planet, it's actually a very, very tiny, thin layer of atmosphere. And that's where 90% of the mass of the atmosphere lies, in this very, very thin layer. Now, one of the other things, I'm just going to a quick revision on the dynamics. Some of you will have come across this before. The key thing is that the Earth is rotating. So in a very simple, if the Earth wasn't rotating, the sun would disproportionately be warming up the equator, and the Earth would be cooling down at the poles. And you would have one simple convection loop that goes from equator to poles, and you would the atmosphere would heat up at the equator and then travel north and cool down at the poles, and you'd have one cycle. But because the Earth is rotating, you end up with these Hadley cells. So there's 3 main cells. And essentially the way to think of this is that it means that around the equator, it is fairly regular, and you have this quite organized convection cell. And the Coriolis force means that the winds are blowing towards the west at the equator. At the polar regions, you also have a relatively simple convection cell that is happening at the poles, and it's relatively stable around, especially in Antarctica, where you've got quite a symmetric, almost circular landmass at the South Pole. The North Pole is a little bit more complicated, but in between these, you have this fairly dynamic cell, which is where all the cyclones and anticyclones are doing their thing. And that's where we happen to live in Scotland, and that's why the weather is always dramatically changing, is because it's always have this extreme mixture, and it's a very 3-dimensional process, this dynamic of the atmospheric circulation. But what this atmospheric circulation is essentially doing is taking warm air from the equator and taking it to the poles where it can cool down, and that's essentially what it's doing. But what you have is warm air moving north and cold air moving south. And in the mid-latitudes, it gets all mixed up. The rotating planet means that you end up with the cyclones and anticyclones forming, and it becomes very dynamic. So we get graphics like this. So when we look at this, and it is definitely this one that's causing problems, but when we look at this graphic, what we see is the what's called the intertropical convergence zone. So that convection area along the equatorial line, and then you can't quite see it from this view, but at the poles it's much more consistent, and then in the mid latitudes you have all this dynamic activity as the warm air and the cold air meet, and they don't want to mix, and it generates lots of 3-dimensional dynamics in the airflow, and that's where we get all this very complicated weather patterns in the mid latitudes that we have in Northern Europe. Right, let me get out of this, see if this works. Oh, my apologies, I should have checked that it was this graphic that was causing the problems, in which case I would have taken it out. So you can't see the screen sharing at the moment. Don't worry, I'm just going to put it back on. So if we consider, so we've looked at the physical composition of the atmosphere and the structure, and that's quite important so that you know what it is that we're trying to measure. It's a significant part of the Earth system, and the dynamics of that are important because it moves energy around. But in terms of the chemistry, most of the chemistry of the atmosphere is nitrogen. So we're about 7 to 8% molecular nitrogen, N2. And that's fairly inert and doesn't do very much. It's not very significant. About 21% of our atmosphere is oxygen. That's a very interesting property. So if any of you have been following the news about Venus and the fact that they found a chemical on the atmosphere of Venus that is very unstable and would suggest that there is something dynamically and actively producing that, and therefore there might be some kind of life, but not necessarily life as we know it, but life in the upper atmosphere of Venus. That is based on a long tradition of looking at the atmosphere of planets and asking questions such as, well, if you look at Earth, why do we have 21% oxygen? Oxygen is a very reactive gas. And if you immediately removed all the life on Earth, the oxygen would be oxidized the atmosphere comparatively quickly in geological terms. it would all end up oxidized in mostly in the rocks. Oxidized in terms of things like iron, you know what happens when you oxidize things. It becomes rusty, it becomes reddish. And so the whole surface of Mars is famous for being known as the red planet, is that's where all the oxygen in the atmosphere has ended up in the rocks, not in the atmosphere. So if there was no life on a planet, you wouldn't expect the oxygen to last very long in the atmosphere. So the fact that Earth has oxygen in its atmosphere is in itself indicative of the fact that there must be some active process that is actively creating that oxygen. And I'm not going to go into that in today's topic, but you should be aware that, well, that's all the photosynthesis and plant activity on Earth, which is actively taking the carbon dioxide out of the atmosphere and converting it into molecular oxygen. And so there are processes on Earth that are actively contributing to sustaining that level of oxygen. If you're interested in looking at life on other planets or the exoplanets and trying to find alien life and all these new planets that they're discovering around other solar systems, being able to measure the atmosphere is one of those key indicators, because if you can find a chemical which is very reactive and needs something to keep creating it, then that is one indicator that there might be some life on it. That's the origin of the Gaia hypothesis. Some of you might have come across the Gaia hypothesis before. I won't go into the details of that, but that was based on looking at the atmosphere of Mars and saying, well, because it's all carbon dioxide and it's fairly inert, there's probably no life on Mars. There might have been at one point, but not anymore, because the atmosphere is nice and stable. There's evidence in the atmosphere of Mars that there is something actively contributing, something like oxygen. So apart from nitrogen and oxygen, the other useful thing that you should know about oxygen is that it's very stable in the atmosphere in terms of oxygen concentration anywhere in the world at any given latitude, altitude, and time of year. We have a very good understanding of how much oxygen will be in the atmosphere at that point. Carbon dioxide changes is much more dynamic and changes considerably across the planet. And the other chemical constituent I haven't mentioned, and this is a dry atmosphere, because the other chemical constituent is water and vapor. So water vapor has a very small contribution, but it varies considerably from almost zero up to about I think it's about 0.1% or something. So there's an extra component in here which varies, which is the water vapor, which is quite a dynamic contribution. So a lot of the gases that we're going to melt down in this less than 0.1% zone, and it's going to be it's quite tricky to, they're very small concentrations. So how do we do that? So to understand how we're going to make these measurements of these very concentrations of gas constituents, we have to understand a little bit about how radiation interacts with gases. So how radiation interacts with our atmosphere comes under a very broad topic of the Earth radiation budget, which I'll mention at the end. One very key component of radiation interacting with our atmosphere on Earth is the clouds, because they have such a large contribution to how much energy is scattered back. But let's look at a dry atmosphere. So let's ignore the clouds for a minute, and we will look at the on this graph here. We're going from microwaves to thermal infrared, near infrared to visible. You should be getting very familiar with electromagnetic spectrum if you weren't already before that. Beyond the violet here and the visible, we get into the ultraviolet. And one thing to note is that, and you might find this in equal measure confusing and annoying, but I'm going to point this out to you just so that you're very clear, is that I always draw these graphs with increasing energy towards the right. And that's because my background is in physics, and it makes sense to do it from low energy to high energy. But many of the textbooks that you will pick up, or many of the websites that you'll look at, will draw these as increasing wavelength. And one of the things that you will find if you do, oh, that was the thing I forgot to mention right at the beginning, is that myself and Steve Hancock are who do the active remote sensing. So if you're signed up for active remote sensing, you will get me again talking about radar remote sensing. And you will find one of the things I'll talk about is that people who do remote sensing are often split into two natural groups. One is the group that came through the historic tradition of cartography and often through geography departments, and are interested in looking at the Earth's surface. They're interested in photogrammetry and mapping and looking at things on the surface, and they will be very focused on the near infrared, thermal infrared part of the spectrum. So all up here. Okay. You will find that there is a radar community and a microwave community that are interested in all the stuff down here. And this group tends to use wavelength, represented by lambda. And this group down here tends to frequency. So you should know already that the relationship between wavelength and frequency is linear and straightforward. Short wavelengths are high frequencies. But always be careful just to check the units that people are using on their graphs. Because for me, I'm always going to be looking at the energy and frequency, because I come from this microwave community. Other people who write books and do websites and give lectures will come from this community and will talk about wavelength, and they will draw this graph the other way around with increasing wavelength. Both of them are perfectly fine. They both have the same meaning. The important thing for you is just to be aware of the fact that we do these drawings differently, and so always look at the axes of any graph that you're looking at, so that you know what you're you know what it represents. In these graphs, I always try to put in a little color thing to show you where the visible is, so you've always got a reference point for that. And what this graph is showing you is how much energy is lost. You'll have seen one of these, I believe, before in various forms. And so what we're looking at here is that that the shortwave is split from round about the thermal. The long wave is from this peak all the way down. And we have what are called the walls and the windows. So we have some windows where we can see through down to the surface of the Earth. And we have these wavelengths or frequencies where we can't see through the atmosphere. Now, one of the things in terms of looking at the atmosphere is that you would think if this is our main wall and we're just looking at atmosphere, because the atmosphere is blocking so much of the radiation, that this would be a great place to look at the atmosphere. In fact, it's not a very good place to look at the atmosphere, because all you see is the top of the atmosphere. You don't see any deeper down. These bits down here, the windows, are great for looking at the Earth's surface. So if you want to do some mapping and land classification and deforestation or oceanography or glaciology, you want to look at these windows. But they're not good for looking at the atmosphere either, because you don't see any atmosphere. The atmosphere has no contribution in the visible part of the spectrum. You see right down to the surface. So if we're actually trying to measure the atmosphere, and we're talking about the chemistry of the atmosphere here, not the gas part of the atmosphere. We're going to talk a little bit later about particles and aerosols. But if we want to look at the gas part of the atmosphere, we don't want to look at the windows. But we don't want to look at the walls either, because we don't see anything. We're going to spend all our time looking at these bits here, which are essentially partly transparent and partly opaque. And these are what's going to allow us to look into the atmosphere. So if I get rid of this and show you a little version. Oh, sorry. So if I represent this graph, that's our Earth's surface in terms of, and we're not looking at clouds. Remember, we're forgetting about clouds because they're particles. We're just interested in the gas of the atmosphere. This is my way of representing that diagram in the background, is that in this part here, the main wall, we can't see anything at all. There's nothing about the atmosphere that you can see. In our windows, and these little windows over here, you can't see any of the atmosphere either because you're seeing right through it. So this is too opaque, and these are too transparent. But the ones that we're going to look at instead are these bits that are semi-transparent, semi-opaque, because that's telling us something about the atmosphere. Okay, so that's just a representation of that picture. And then the other thing, just to remind you, is that you can flip this round. So this is the amount of energy that is lost. So this is the attenuation through the atmosphere. You can flip this diagram, and you'll see this diagram shown in as a indicator of how much energy is passing through. So that's 100% transmission at the top here. The information is the same. You've just flipped it top to bottom. So this kind of diagram, just always be careful to watch both the the x-axis and the y-axis to make sure that you're looking at it the right way, because you will find that these graphs are flipped both top to bottom and left to right. It's exactly the same information. It's telling you exactly the same stuff. It's just that it's represented in different ways depending on what the particular narrative is at the time. And that's your atmospheric windows, and it's your major wall there. Right, another thing we have to think about is when we're looking at radiation, what are we talking about? There are two major ways in which you will hear people talk about electromagnetic radiation. One is in waves, and the other is as particles, so photons. So the corpuscular model of light, as it was called. And through the sort of 18th, 19th century, there was lots of debate about which it should be. Should it be a wave description or a particle description? And when quantum physics came along, it ended up with something. It was a mixture of both. It was little packets of waves. So if you can imagine what we're talking about are little packets of waves, so photons that have a wavelength, then that's the way about the conversation we're about to have about radiation and gases. And my analogy for this, and the way that I represent this in terms of pictures, is to think of little musical notes in terms of wavelengths. So each of these is little are colored differently to represent their different notes. So that I should have got a little musical instrument or something, but that can be a do do do, different notes as representing the different frequencies or wavelengths of these little packets. Okay, and what we're going to do is think about these as our little photons, and each of these photons then has a wavelength, and you can think of those wavelengths as in terms of frequency, and so therefore our notes, musical notes. And that's one way to think about what happens with molecules or atoms. And just to note, I'm going to talk about molecules in general because the things that we tend to be looking at are molecules. So H2O or CO2 or O3. So they're all combinations of atoms. But what I will be describing applies equally to atoms as well as molecules. Okay, but I'm just going to use molecules rather than always saying atoms or molecules. So just remember that that it applies to atoms as well as molecules. But so in terms of a molecule absorbing a photon, when does a molecule absorb a photon? Well, the key thing is that it will only absorb photons that have got a frequency that corresponds to one of their matching frequencies. And because frequency is related to energy, essentially it is related to, well, it's only going to absorb when a photon comes along that's got just the right energy, and it will absorb it. So here's my next demonstration. So if you've got your wine glass handy, let me just stop sharing. All right, so it's back to looking at me. So here's my wine glass. It's just water because it's not wine o'clock yet, which will be a bit later. And some of you will have done this trick before where you wet your finger. I hope my microphone is good enough to you can pick that up. Yeah, those of you who've got your camera on, can you just nod or something? Yeah, so you can hear it. I see some nods. Cool. Right, so that's a particular frequency. And somebody, I can't remember who it was now, who was asking about whether or not your glass has to be full or not. But that's, if you remember that frequency. Oh. That's too similar. I should have checked that out before. But the caricature that you know is that if I could sing that note, perfectly, this glass would start to vibrate because it's the resonant frequency of the glass. And if I could generate energy through my voice that was just at that frequency, and I'm not a good singer, a good enough singer to do that, but if I could make that glass start to vibrate at its resonant frequency, and it would keep absorbing that energy until eventually it would just shatter and break. And that's my analogy for what molecules are doing in the atmosphere, is that if it's got that frequency, if the sound has got that frequency, then this will vibrate and adopt the energy. If it doesn't have that frequency, it will just ignore it and it will just pass by. So that's another, if you haven't done that with a glass before, you should do it. And in fact, if you're in the student rooms that I've been in before, the kitchens usually have just lots of old glasses of very different sizes. So you can try lots of different sizes and see if you can get different notes out of them. Right, let me share my screen again. So think of these molecules in the atmosphere as having these resonant frequency. That's the only one it wants to. It will only interact with those frequencies. I'll have to go through this again. Sorry, but and the same is going to apply when it comes to emission. Okay, each of our molecules, like our glass, has a particular frequency that it resonates at, and that resonant frequency is going to be the only frequencies that it emits. Now, the other thing is that if we have multiple together, so if you have a couple of different molecules, so this is a gas made up of different molecules, and if you have lots of different wavelengths represented by these colors, all these different frequency notes as they come by, it will absorb some of them, but it won't absorb the other ones. So the ones that don't match the particular resonant frequencies just go through, but the specific ones that match will get absorbed. And the emission is the same, so that these molecules will only emit these particular wavelengths because that's their resonant frequency. Now, the useful thing for us is that any particular gas molecule has a particular resonant frequency. I'm going to talk a minute about the fact that it has multiple resonant frequencies, but for simplicity, let's just imagine it's got one resonant frequency like this glass at the moment. But this glass versus that glass, they have different resonant frequencies. Okay, and in fact, if I'll just hold on one second. Sorry, I should have had another glass handy. Right, so I've got two glasses now, and they both have different frequencies. Okay, so if we've got two different molecules, one's carbon dioxide, one's ozone, is that if we look for those particular resonant frequencies, either as emission or absorption, then we can be confident that we're only looking at that particular chemical, okay? Because all the different molecules, like different glasses, have their particular resonant frequencies, and they only absorb or emit at those frequencies. And like I say, we're going to talk in a minute about the fact that actually carbon dioxide has multiple resonances, not just one. But for our nice analogy just now with the glasses is that each style of glass is a different kind of molecule, and each of them has a different frequency. Now, it's not just an exact, when you look at this diagram, this is 100% transmission. We've got some CO2 gas, and it is absorbing that particular frequency. So one specific frequency happens to be in the thermal infrared here. And the way I presented it, it's going to be at one single definite frequency. In actual fact, it's smudged. So it's got a width to it. And one of the main reasons, there's two reasons for that. One is because of pressure. So if you increase the pressure, you get it gets into the level of quantum physics that I don't want really to discuss, but the pressure fudges some of that. Basically, if you imagine pressurizing this glass so that it changes its shape slightly, the frequency might be a slightly different. So you get slight variation. But the other one to realize is that you get what's called Doppler broadening. So this particular line for carbon dioxide will be a bit wider because some of the molecules are moving towards you, some are moving away from you. And because of the Doppler effect, it will slightly change those frequencies. So the Doppler effect, just to remind you, is when you've got a relative motion. So when a very fast car comes driving past you, it goes, so the pitch of the engine noise changes as it goes from moving towards you to moving away from you. If those individual molecules, so a gas made up of all these carbon dioxide molecules moving around, some are moving towards you, and so instead of this note, this particular note, it will be a slightly, oh, I can't do it. It'll be a slightly higher note. It'll be even higher. If it's moving away from you, it'll be lower. And so what you get is a bit of a spread in the line. So it's never an infinitely narrow line. It's always kind of fudged a bit. Now, if you've got a gas that's absorbing at that particular frequency, and we know that particular frequency corresponds to a resonant frequency of carbon dioxide, then if you have lots of carbon dioxide, it will give you a very deep line. The absorption will be very strong. And if you don't have as much, you'll get a much shallower line. So the depth of the line, so if you're looking at absorption through the atmosphere, the depth of the line actually gives you an indication of how much carbon dioxide would be in that. The scenario of how we're going to make that measurement from satellite, we'll talk about a bit later. For now, it's just a case of thinking, well, if I look at the absorption if I have light coming in through the atmosphere and I look at how much is absorbed at this particular frequency, I will determine how much carbon dioxide there is. If I look at a frequency that's specific to water vapor, then I'll be able to determine how much water vapor there is. And you can actually see that if you look, I've got a little bit of equipment that I bring to classes, which I won't be able to do. I've had a look at it in the oh, it's not there after all. I've had a look at it to see if I could do it with the camera here, but it doesn't really work. But you can, if you even look at in detail at the light that comes from the sun. So the sun is emitting across the visible part of the spectrum. It emits beyond that, beyond the ultraviolet and into the infrared as well. But in terms of the visible part of the spectrum, the upper atmosphere of the sun is actually a gas rather than a plasma, and it is absorbing some of the light that comes out from the sun. And you can actually see these individual lines. I've exaggerated them here in this diagram, but you can find these individual lines of absorption in the upper atmosphere. You will also get absorption in our atmosphere. So if you could have a spectrometer that looked at the sunlight coming in, you would find that there will be lines associated with carbon dioxide and water vapor and the like in the visible spectrum that would absorb the radiation. Now, it's quite possible that Caroline will talk to you about some of the very new sensors, which are which can actually look at these lines, these absorption lines, which are very, very narrow. But it means that even in daylight, if you look at a particular wavelength of visible light, you will find that for some of those lines where there is a lot of absorbed upper atmosphere of the sun or in our own atmosphere, is that those lines are actually the lines are very dark because the atmospheres are absorbing those particular wavelengths. So you can look even in daylight at some visible wavelengths and you will see that there's no sunlight because essentially all the light has been absorbed. And you can use that technique for looking at the Earth's surface because essentially it means you can look for very, very faint signals in some of these dark lines because there's not any sunlight because it's all been absorbed by either the atmosphere of the sun or the atmosphere of the Earth. If we look at gas emission, so imagine going into the dark and looking at what's emitted. And again, I've exaggerated this for effect because in order to get emission lines operating in the visible part of the spectrum, you have to heat the object up quite considerably. But there is one place that you actually can find that where you're heating up sometimes gas or other elements in order to generate light, and that is through in light bulbs. Now, LEDs are very good at showing you a very constant signal. But if you can find old lights like some of you might have even come across the old sodium lights that were the street lamps, and they had very distinct, looked quite yellow. And you could actually, if you looked through a spectrometer at that light, you would find that it wasn't a full spectrum. It just had particular components of the sodium emissions. So this is two ways that we can start considering how we can extract information about a gas. One is to look at absorption and what gases are absorbing the light coming through it. And the other is to look at emission. So what gases are emitting radiation. And the shape of this shape here in terms of the atmospheric walls and windows, this is actually composed of many, many individual lines of different chemicals in the atmosphere, mostly dominated by water vapor, carbon dioxide, oxygen, ozone are doing most of the absorption across this kind of graph. Oh, yeah, I thought I was going to have that. So carbon dioxide, water vapor. So this bit in the middle, this is what's called the water vapor continuum. There's so many energy transitions going on here for water vapor that it's almost continuous. Also, what I should have said here is we're now moving into this scenario whereby our individual molecule doesn't have just one specific frequency, resonant frequency. Okay, so in this example, our molecule represented by a glass just had one resonant frequency. We're now moving to this scenario where, in fact, our glass analogy doesn't work anymore because our molecules actually have multiple resonant frequencies for different reasons that we're going to talk about in a minute. So water vapor, for example, has these multiple energy transitions which correspond to resonant frequencies across from the near infrared right through to the microwave. And the last one is variations of oxygen. So molecular oxygen, the O2, and ozone, which is O. And ozone, the one that you're most familiar with, of course, is that in the ultraviolet, the ozone molecules are absorbing a lot of violet radiation that comes in from the sun. And that's why we consider them very important in terms of life on Earth, is that if you get rid of the ozone, you would increase the amount of ultraviolet radiation arriving. And that has potentially a damaging effect on biological material. And any of you who have been to places like Southern Australia or New Zealand will know that when that big form of the ozone hole starts to form in the Antarctic springtime, is that if it reduces the amount of ozone over land masses in Australia and New Zealand, they actually tell you that that's happening. So they put on extra sun cream to make sure that you're blocking those ultraviolet rays. So this shape of this diagram, that's where it comes from, is it's the constituents of the atmosphere, each of which have got these individual resonant lines or collections of resonant lines, and each of those lines is widened by pressure and temperature, and so all together it makes up this shape of the absorption through the atmosphere. Well, one last thing I wanted to mention here was this graph I kind of hand drawn. It's a bit wiggly. Okay, what I want to show you, if I show you a section of this graph and we look at it in close up, what we find is that it's far more complicated than my diagram. So each of these little peaks here is an absorption line associated with either water vapor or ozone or nitrogen or oxygen. And you'll see that especially on this blue line here, there's lots of tiny ones. In fact, it's extremely complicated. But each of these little peaks here, somebody's asked a question. So Seamus is asking about whether it's related to tungsten-based film giving off a blue tint in photography. I'm not sure about the tungsten-based film, certainly because tungsten I would normally associate with a light. And it may be related to the color sensitivity of whether or not you have, are you talking, Seamus, are you talking about the actual film, so photographic film?
Yeah.
And so are you referring to the fact that you can get film that's for indoor light versus outdoor light?
Yeah. But
okay, so
tungsten film.
So one of the things that we'll come to in a second, and one of the reasons why I won't do the measurement live, I've got some pre-done stuff, but you guys can do it live. Modern video cameras and static cameras will actually adjust for this slight difference in color of the lights, and if you're trying to do something that's got very subtle color differences over video, then it doesn't help if it's proactively trying to make things look white. Now, what you can't see here, but I'll describe to you, is that one of the lamps that I've got in this room is actually I think it's a halogen, I think possibly, but it's certainly orange. It looks quite orange. Whereas these LEDs, got white LEDs that are in the ceiling, so they're very white, and I can see the difference with my eye when I compare them. Now, your human eye is really good at adjusting for that. So in the evening, and you're inside, and you're just using the sort of very yellowy lights, your eye adjusts for that, and everything still looks white. But and if you go outside, it's very white. The sunlight is much whiter than typically most indoor lights. If you're using photographic film, your photographic film is clever enough to tell the difference between inside and outside, and it doesn't automatically adjust. So if you're using indoor lights, you often, certainly in the days of photographic film, you would have film that compensated in terms of the sensitivity to make it look whiter than it would otherwise look. This is all changing now, essentially in the last few years, because LEDs have become so cheap, and you can make LEDs that are really white. Now, bizarrely, you also get LEDs that purposefully make them look a bit more orange so that they just match in with all your other lights in your house. Or you can get LEDs that are very, very much whiter. So if you can get lighting which is replicates more of the white light from sunlight, then you wouldn't need special photographic film indoors. It's just the fact that historically, and even today, some of the LEDs and lights you get won't necessarily be white. And this is one of the, if you can get, and I've forgotten where I've actually put it, but I've got a little sort of just a spectrograph viewer. It doesn't cost very much, it costs a couple of quid to get them on Amazon. And you can spend all day wandering around, looking through it and seeing, certainly in the visible part of the spectrum, what the differences are between all the lights. So typically that's the one thing that I can't do, that I would normally do with you if I was physically there in the lecture room, is actually going and get you to look at the lights and seeing the difference between LEDs and strip lights are really old light bulbs, which can be quite different. Does that answer your question, Seamus?
Yeah, it's brilliant. Thank you.
So in this part of the spectrum, though, in terms of the slide that we're looking at, this is into the microwave, and it just shows you just how much activity there is there. And these diagrams that you'll see in the books and the ones that I showed you are quite simplistic, and often because it's just trying to show the difference in the walls and the windows. But we want to look very specifically at what these very subtle variations, because each one of these little peaks corresponds to one of these resonant frequencies of a molecule. And it means that we can look in detail. If we just look at these particular frequencies across some of these peaks, we will get very specific information just about that particular molecule. Some of these overlap. Okay, some of them get very close together. Some of them are quite distinctively on their own. And some of them are, so this one here, for example, is a very strong water line. It's the 183 gigahertz water line, which is used a lot for measuring the atmospheric water context. And you notice here it actually even refers to the oxygen resonance and the water vapor resonance. So my analogy with the glass is not as far away as you might think. It is about these resonant frequencies. And so at these little peaks, this is where these individual gases will absorb and emit, because that's the specific fingerprint of these frequencies is what we're going to look for in the atmosphere. Now I'm going to talk a little bit more about some of the specifics and some of the examples of what is actually changing, what causes these resonant frequencies. Why does a molecule want to absorb or emit at one frequency and not another frequency? And one model is to do with electrons shifting in orbit. So this is a classical model of an atom. It's got a nucleus and it's got an electron in an orbit. And that orbit, so it's in the second highest orbit here, is that if an electromagnetic wave comes in, so a little pulse of wavelength comes in, call it a photon if you like, it jumps up into that higher orbit now. So it's absorbed that specific frequency because it corresponds exactly to the energy jump between that orbit and the next orbit up. Now you have to get into the details of quantum physics to look at why exactly there's specific discrete orbits and not every possible kind of orbit. The key thing for you just to realize is that there is, for any atom or molecule, there's a set number of orbits that the electron can be in. And if it jumps from one to the other, so if it will only absorb, this electron here will only absorb that one resonant frequency that matches the energy step from that orbit up to the higher orbit. And so if you look at this set of orbits, this is 4 orbits here, and there's 6 different energy jumps. So an electron, in terms of going from one orbit to the next, it can just go up to the next higher orbit, or it can jump up 2 orbits, or it can jump up 3 orbits. So it's free to move across all of these orbits, but it has to stick in one of them. But what it means is that there is a set, in this case, of 6 discrete energy jumps that it can do. And for each energy jump, that corresponds to a particular frequency or wavelength. And so it's not just one resonant frequency here, it's six resonant frequencies. So at any of those 6 frequencies, this molecule or atom would absorb those wavelengths at those particular frequencies. An emission is the same thing in reverse. So it's at a higher energy level, and then it jumps down. And as it jumps down to a lower energy state, it releases a photon. And so these energy jumps now are just the same jumps, but in reverse. So if it goes from a higher energy orbit to a lower energy orbit, it will emit a photon of that frequency, so of that energy. So any particular molecule has this specific footprint of resonant frequencies that it can match with, and that's what creates this particular pattern. So any particular gas has a set of a fingerprint of a set of wavelengths that it will either absorb at or it will emit at. So if we take carbon dioxide, for example, it may have multiple lines, different energy jumps that it can jump up and down from. And this is now looking at emission. The last diagram I showed you was to do with absorption, and the same processes apply in terms of emission. So in terms of emitting radiation, you've got the one specific, if you look at one resonant frequency, because of pressure and temperature, it's actually broadened, so it has some width to it. And in this case, in terms of emission, it is definitely the case that if you have lots of the gas, you will see more emitted radiation. And if you have not so much of the gas, you will see it emit much less. The problem we have here is that that's also the case for hotter or colder gas. So if the gas is warmer, it will emit more radiation. If it's colder, it will emit less radiation. But also, if it's got more of that particular molecule at that frequency, it will emit more. And if it's got less, it will emit less. So one of the key challenges and one of the difficulties with sounding or measuring the atmosphere is that if you're looking at the emitted radiation, you have to separate out what is the temperature effect and what is the concentration effect. We've talked about that, so the breadth of the line, and then the challenge is how do you, if you're trying to measure emission, how do you differentiate between the concentration and the temperature? Now, one of the particular sneaky ways that you can solve the problem of temperature and concentration is that you use, well, one way is that you look at the line broadening. So you look, you have a much more, you make multiple measurements across the entire shape of the emission line, because the width of the line will help tell you something about the temperature or the pressure. Clever thing you can do is, if you remember earlier, I said that oxygen is fairly consistent and regular and well defined in terms of its concentration. So one of the things that we do is that we measure. So if I go back to let me jump out. If we go back to this diagram, one of the clever things that we do, certainly in the microwave part of the spectrum when we're measuring the atmosphere, is that we measure an oxygen line. And the reason that we measure an oxygen line is because we already know what the concentration will be. If we know what the concentration is, then any changes in the emission line of oxygen will be indicative of changes in the temperature. So we can retrieve the temperature from the oxygen line. And then once we know what the temperature profile is of the atmosphere, we can look at, say, a water vapor line or an ozone line, and we'll be able to determine the concentration because we already know what the temperature is at that particular point in the atmosphere. Right, and the final thing I wanted to say about that was that is to emphasize that the electron transition, so the idea of electrons jumping up and down in orbit, is one way to think of the energy transitions, but that's typically what's happening in the visible near infrared, far infrared. When to the microwave part of the spectrum, it's mostly to do with molecular motion. I'll show you some examples of what I mean by that. Once you get into the very high energy end, you can get into energy states that are actually in the nucleus of the molecular atom, and they become much higher in terms of the energy. So, but for us, in terms of remote sensing, we're mostly interested in the electronic transitions with the electrons jumping up and down in orbit, and the molecular motion. So if we look at carbon dioxide, so carbon dioxide is one carbon and two oxygens, and it means that the actual molecule has these vibration and rotation states. So it's almost a better analogy for the glass with the resonant frequency, is that these molecules, so they have three rotational and three vibrational states. And water vapor is similar. So H2O. H2 is the two hydrogens and one oxygen. And it has rotational and vibrational states. And each of these has each of these is vibrating in slightly different ways, and so they have different energy. And that's where you get a relationship between the dynamics of the gases bumping into each other and the different energy states that they can get knocked into. And each of these is a different resonant frequency for the molecule. So the 183 gigahertz, for example, I believe is a rotational energy state. But the key summary diagram is that you can represent these energy levels in this kind of diagram, where you've got energy up the side, and what you're doing is that you're representing the different energy contained within the molecule. Well, and my presentation has decided to stall again. That'll give me a minute to have a glass of water. And I'll quickly check if there is any chat. Right, let me have a look at some of the questions that have come up. Is it because of isotropic property of atom that we're observing multiple resonant frequencies? It's possible that you've just had that answered. So Chandra, Molly, if you've had that answered now, if you let me know, that'll be helpful. Just take that back. When observing, does the frequency absorb return strong or weak signals, since you mentioned it's also emitting at the same frequency? So that's when we get, I'll talk about that a little bit later when we look at the Earth radiation budget. So you've already touched on earlier lectures on the black body radiation. And so in terms of emission, the object has to be hot enough to emit those higher frequency or shorter wavelength emissions. Typically, an object, as it cools down, it will be, if the object is quite cold and doesn't have lots of energy in it, it will come, and if I show you this diagram, this is your representing the, on the left, the absorption, and on the right, the emission, is that to get a high energy state, high energy emission, you would go from a high state to a low state, for example. To get your molecule into that high energy state in the first place, typically it requires lots of energy, either because it's being bombarded by photons or because it's getting bumped into by other molecules next to it, which are very hot and have high kinetic energy and are knocking things up into higher energy. So you can have this conversation in the context of black body radiation and note the fact that, well, as it gets hotter, more of these molecules are going to end up in these higher energy states. And therefore, when they drop down, there's more chance that they will emit higher energy photons. And so that's where you get your black body radiation curve that goes to a peak at higher and higher frequencies as the temperature increases. Does that mean more complex molecules or higher Z atoms have more possible energy jumps and more resonant frequencies? The specifics of that, that's sort of high-level chemistry and molecular physics, which I'm not sure I can answer that effectively, Ewan, because water vapor, for example, has a huge number of resonant frequencies, and that's what makes that huge water vapor continuum across the very long wavelength radiation. And it's not necessarily a particularly complex molecule, so I don't know exactly what it is that causes that. And the last time I looked, which was many years ago, I'm not sure anybody quite understood why it had quite so many resonant lines in that region. Anyway, the quick link back here is that you can actually calculate what these energy states are, and you can look at the different jumps between one energy state and another energy state. And as a result, you can calculate out what the frequency would be for a particular jump, so a jump from 1 to 2. And that's because we know that the relationship between energy and frequency is a linear relationship with Planck's constant h as our factor in there. So you can directly relate these energy states into particular frequencies. So that's what I was just representing here, and the fact that across even the visible spectrum, there are many molecules that have resonant frequencies and are absorbing in these lines. And I'm pretty sure that Caroline is likely to mention the work that's done in particularly in the oxygen absorption lines, where you then have very much less sunlight, and you can look at very fainter signals as a consequence in these lines, because the atmosphere has absorbed a lot of the sunlight. Right, let's take a quick comfort break before we do the last part. The last part, you've done all the hard work now, okay? That's all the heavy lifting. For those of you who remember the Karate Kid, that's all the wax on, wax off stuff, okay? Now it's relatively straightforward to take that information and put it into some observational scenarios. So we know that the atmosphere will absorb at particular frequencies, depending on what gases are in the atmosphere. And we know that it will emit at certain frequencies, depending on what's in the atmosphere. The emission also depends on how hot the atmosphere is, so the temperature will have a difference. And we also have to consider about the fact that we're looking through a volume. The atmosphere has a thickness, and we might be interested in looking at the vertical profile. So how might we do that in the atmosphere? And so that's going to be the last part. But as you can hear, my voice is getting a little bit croaky, so I'm going to take a little break. So if I stop sharing and let's have a look at the clock. Right, it's 11:20. Let's come back at 11:30, so 10 minutes. So let's come back at 11:30, half past the hour, because I realize some of you are in different time zones. So at half past the hour, and then we'll do the last section, which is not very long, but has some fun. And this last section is the one where if you want to try the milk experiment, you want to get a glass, a big glass, like a pint glass, full of water, very small amount of milk, and a light bulb of some kind, or a torch. Okay, see you all in 10 minutes. And again, if you've got questions, or if you're thinking of questions that come up, put them in the chat. I'm just having a look at that. Does the phase of H2, ice, water, vapor, and liquid water affect its resonant frequency? That's a very good question. When it's solid or ice, it has very different resonant properties. So what we're talking about in here is very specifically to do with water in or everything in its gas form. At the end, the end of this section, we're going to look at scattering and how that has a different effect. Well, I think that's all the questions I've answered, but keep adding questions into the chat if you've got them. Right, see you in 10 minutes. Right, we're all ready for the last section. One of the things I should have said is actually that in these breaks, I want you to get away from your screen and go and do something. It's too late now because we might not have another break. But as a tip, just because I realize that everybody's looking at screens much more than normal, is that you can get software that you can install, which actually reminds you to get away from your screen every so often. So I've got a piece of software called Timeout, for example. So every 40 minutes, it basically fades away the screen and reminds me that I have to go and do something else for 5 minutes. And so I've got 5 minutes to go and read a book or get a coffee or do something away from the screen. If you would like to look after your eyes and make them last a longer time, would thoroughly encourage you all to install some software like that and make sure that you're not constantly looking at the screen from morning to night, because that is the risk with all these online lectures rather than physical lectures, is that where in normal circumstances you would be physically in a classroom not looking at a screen, you're looking at a screen, and then you're looking at a screen the rest of the day as well. So that's my tip for the day, is to encourage you all to install a bit of software to keep reminding you of that. Right, last section. How are we going to turn all this theory into practice? So we're going to have a step. Our first step is to think about specifically the observational scenarios that we might use. and then I'm going to talk about scattering, and then we will do the actual geometries by which a satellite would make these measurements. Right, so in terms of our setup of what we're going to do, here's our atmosphere middle. One setup we're going to do is just we're going to measure the emission from the atmosphere. There's a couple of ways in which the geometry that we might look at that, of how do we look at the atmosphere? Do we look straight down or do we look at an angle? And we'll look at that in a second. But we're specifically looking at emission from the, I just realized that that shouldn't be there. So we're gonna look at the atmosphere, and because the temperature of the atmosphere is less than 300 Kelvin, there's not going to be very much being emitted into the near infrared or the visible. Most of the emitted radiation is going to come in the thermal infrared or in the microwave part of the spectrum. In between the thermal infrared and the microwave, there are places where it's emitting radiation, but that's in the water vapor continuum section, whereby it's all just coming from the top of the atmosphere. So you're not seeing anything deep. All you're seeing is a saturated water vapor in the atmosphere. It's not as useful as we would want. So looking at, we might also look at absorption. So we can look at emission, and we call that sounding. So we're looking at the emitted radiation, but we might also look at the absorption through the atmosphere. And if we're going to look at absorption, what we need to take into account is that we need some source that's coming in from the back end of the atmosphere. So radiation is coming in behind the atmosphere, it's going through the atmosphere, and then we're looking at what comes out the other end, and we're looking at how much of that radiation is absorbed. Now, the sources that we might use for that, we're going to use some convenient sources that already exist, such as the sun. So the sun is a nice bright source. We can measure that, and we can look at how much is absorbed through the atmosphere. We might look at stars. Stars are other suns just far away. And we might also, in the microwave part of the spectrum, so the microwave and radio, just use natural signals that occur. So things like GPS, or just generated signals from other satellites. When investigating the atmospheres of the other planets in the solar system, for example, when you send out a probe, one of the things that you do is have it transmit a signal as it goes behind, say, Jupiter, and you can track the absorption as that signal sets behind the edge of the atmosphere of the planet. But the other thing that we're going to look at is scattering. So energy comes in and it's scattered. So what do we mean by scattered energy? And that's it's not emitted, so it's not dependent on the temperature. It's not absorbed. This is just energy. So one of the key things about scattering is that it's not absorbed and re-emitted. It's just that energy is redirected. So the individual photons that come in will inelastically bounce off the off the molecules and get sent off in different directions. That direction could be forward scattering as well as back scattering, or scattered off to the side. Now, the properties of scattering, one of the things that we need to look at is a diagram a bit like this. And the key thing here is these two axes. So this axis, in terms of what this is representing, is what's called the scattering cross-section, but it's normalized by the actual physical cross-section. One way to think of this is how much energy is being scattered, essentially, in proportion to the actual physical size of the object. Once it gets to a value of 1, is that the amount of scattering corresponds to the actual physical size of the object. When it gets to lower values down here, what it means is it's scattering much less than the size of the object suggests it should be scattering. Along the other axis, this is essentially the wavelength. but it's the wavelength in proportion to the size of the object. So you'll notice that it's got an R here. So this is a hypothetical scenario where you've got a spherical object, and that spherical object has got a radius. Well, if I put a little arrow on like that, it's got a radius of R. So R is the, can I move that? There we go, R. So we're assuming it's a spherical object with a radius R. So what we're doing here is pi r squared is the physical cross-section of that sphere. So when the physical cross-section equals the measured cross-section, it's got a value of 1. And along here, it's 2 pi r, and 2 pi r is the circumference of the circle that's the cross-section of the sphere. So one whole grand circle around the great circle around the sphere is 2 pi r divided by the wavelength. So this is a proportionality measure to do with the size of the wavelength and the size of this object. Instead of doing the proportionality just the radius in proportion to the wavelength, the physics of it is actually more correlated with the circumference. So we use 2 pi r divided by the wavelength. So when the circumference of our sphere is the same size as our wavelength, we get this first little peak. Now, some of you will have seen this diagram before. Sometimes some of you, this will be the first time. I don't want you to worry too much about what's happening in here. Okay, it gets very complicated and it's very interesting, but it becomes very sensitive to changes in wavelength. So if you have one size of object and you change the wavelength, it gets very complicated here. This is in what's called the me scattering or my scattering. If any of you have had the luck to see what's called mother of pearl clouds when you're up a mountain, that's because the size of the water droplets in the mist are now small enough by this very wavelength sensitive pattern, and you get nice striking color streams within the clouds. If I'll get somebody puts their hand up if they've ever seen mother of pearl clouds. I'll get to that in a second. It's quite rare, and you'll remember it if you've seen it. But the two extremes that we're interested in are the what's called the optical scattering. So that's at this end, and the Rayleigh scattering or Rayleigh scattering, which is down at this end. Now these two are the two extreme cases, and they're the most interesting from our perspective in looking at scattering from the atmosphere. The optical scattering, you'll notice that there is no variation, there's no change. So as you change this, whether you change the size of the sphere or the size of the wavelength, if you're in this domain, it really makes no difference in terms of the scattering. And what that means is that you can change the size of the object, or you can change the size of the wavelength in this region, and it has no impact. The scattering is the same. So it's the same across lots of different wavelengths. And this occurs when the object, so if I get rid of this and redraw. So at this end, you've got large objects and short wavelengths. Okay, at the other extreme, into the Rayleigh scattering, what you've got are small objects and long wavelengths. Okay, so if your object is, if you're looking at the same wavelength and your objects are very, very small, you're going to have Rayleigh scattering. If you're at the same wavelength and you have a very large object, you're going to get into optical scattering. Likewise, because this is just a relative measure along the bottom here, is that if you have the same size of object, but you have very long wavelengths, you won't get very scattering. So if you're in the Rayleigh, if you're in this zone here, for the same size of object, the wavelength will have a big impact. So as you change the wavelength, you go along this axis. So it changes that considerably. If you're in the optical scattering zone, a change in wavelength has no difference. So short enough, if your wavelengths are all short enough and your object is very big, comparatively, is that there'll be no variation due to color. The wavelength will make no difference. The scattering will be the same. And this is where we have examples such as clouds. And what we're going to see in a minute is milk. Okay, so these are examples where clouds and milk are made up of relatively large droplets. Okay, I'm going to describe what milk is in a second, but they're because their clouds have got relatively large droplets of water, there is no color to them. The sunlight comes in across all the visible parts of the spectrum, and all the visible part of the spectrum are scattered equally because the objects are so big. In the Rayleigh part of the scattering zone, in this zone, is that we have if the molecules start to get, or the scattering object is small enough in the size of the wavelength. So compared to in the visible part of the spectrum, if we are at hundreds of nanometers, if we've got something that is in the size of a few nanometers, then it's going to be much smaller than all the wavelengths in the visible part of the spectrum. And what that means is that the shorter wavelengths will scatter more than the longer wavelengths, and the longer wavelengths are into the red. Remember, this is 1 over the, or this is 2 pi r over the wavelength. So this is longer wavelengths down here. They barely get scattered at all. And this is where we get, and certainly through here, I don't know what it's like in Edinburgh, and certainly don't know what it's like in China, but there's blue skies and white clouds just now. So the white clouds are up here because they're large droplets of water scattering the sunlight across all the wavelengths of the visible light. Whereas the blue sky is interacting with the molecules of nitrogen, which are a few nanometers in size, and therefore the blue bits get scattered a lot. The blue bits get scattered a lot. The blue wavelengths get scattered a lot, and the red wavelengths don't get scattered. And so the sky looks like it's blue. So this diagram explains what you see in the sky. And we can use this effect to also look from space, looking back at Earth, to look at object scattering. And all those aerosols that we listed at the beginning will range in size that are comparatively small to comparatively large compared to the wavelengths that we'll look at. Or we can look at longer wavelengths into the near infrared or even the far infrared. And that sensitivity wavelength to particle size will give us an indication of what's happening in the atmosphere with the particles. And so this was just a little animation to illustrate the fact that all the longer wavelengths, the red ones get passed and the blue ones get scattered. And so that's what's happening in our atmosphere. Right. Our final home experiment of the day involves milk. Right, so here's a glass of milk. Not a glass of milk, it's a bottle of milk, because I get milk delivered in glass bottles that are reused and it saves on plastic. So I can recommend everybody doing that if you can. But the milk looks white, okay? So any of you have milk at home, you can go and have a look at that. And you've seen milk, so it looks white. And the reason it looks white is that it is an emulsion. And the key thing about milk is that it's an emulsion of suspended fat blobs. Basically, you've got big droplets of fat that are suspended in the liquid, which is mostly water. And these large particles of fat are large enough to be optical scatterers. So the light that comes in scatters that light equally, regardless of wavelength. And that's why it looks white. You illuminate it with white light and it looks white. Now, some of you may have come across, and just recently I came across an interesting experiment that somebody was describing that basically showed how milk was actually acting as a Rayleigh scatterer. Okay, so Rayleigh scatterer being over in this part of the diagram, and saying that they could show the Rayleigh scattering in milk. And I thought that's not true, because I'm very confident that milk is an optical scatterer. So I did this experiment. So I'm going to try this experiment and see if anybody, put up your hand if you've got some milk in a pint glass of water, and you're going to do this experiment with me. Any hands? Oh, a few hands. Yeah, a few newbies carrying, man, are going to give it a go. Right. I'm going to have to turn off all my lights first of all. Going to make this dark. So what I've got one, a pint. It's a bottle of. It was a bottle mostly of water. Okay, so it's about half a liter of water in this bottle. If you've got a pint glass, that's it's about twice this, but you want to have it with water. And you'll notice that it looks quite white. And the amount of milk I've actually added to here is only about half a teaspoon. So if you're ever having arguments with climate change deniers who say, oh, the concentrations of carbon dioxide are so small it can't possibly have an impact, get a pint of water and put in like a drop of milk. Okay, so that, because the amount of milk I've got in here is 1% of the total volume, and it's quite clearly almost opaque as a consequence of 0.5%. So it's quite, I haven't actually experimented, but you could put in probably as little as 0.1%, and you'll still see the visual difference of that. Now, the experiment that I found on the internet and various books basically said, well, milk is a Rayleigh scatter. And you can show this by looking at the scattering. If you scatter for light from the side, it will look blue because it's mostly scattering. But if you do light through it, it will look orange or reddish because all the longer wavelengths are getting through and the blue light is being scattered. Now, I haven't tried this on the camera. As I explained earlier, it's possible that this doesn't work because the camera here might automatically adjust for the color balance, and therefore any subtle color variations will be.
Ian, when you held the bottle up with the light coming from the back, from your window, it looks blue.
Yeah, it does a bit, but hang on. This is part of the problem of and why I haven't experimented with whether Zoom automatically adjusts the color balance. But I'm going to show you what to do, and then I'm going to show you some pictures I did where I made sure that the color balance was correct, and you can experiment with this at home. Now, the key thing is that it is a very small amount of milk, right? So this is about half a teaspoon in half a liter, all right? And the way to experiment if you're doing this is start off with not very much and then keep adding. But let me see if I turn that, I make this it's not completely dark, but let's see if this works. So I'm just using the light on my phone. Yeah, and if see, that's not, I'm not entirely, it looks bluish for me, but that's my guess would be you'd be less convinced about that. Oh, it looks quite blue. If I shine it from the back, see, getting the balance of that's quite difficult. See, if I look at that, well, maybe up here, I can't adjust the exposure or anything on that, so it's difficult. I think it's something you folks have to just try at home. Does that work? Man Chen is showing me what she's doing, but I will. That's the theory. So the problem here is that I can see it. It's just the color, the balance, getting the balance right on the camera doesn't work so well. I'm going to show you the results of an experiment I did where I actually got into a darkened room and I could adjust it. Whoops. And then I'm going to explain to you what's actually going on. Now that, so just to be clear, I cheated on that one. That's got more milk in it than the next two pictures I have. But I just wanted to show that it's under normal sort of illuminating conditions. When you actually have lots of milk in it, it is definitely white, and you can't do the other ones. But here, and this is where you got to sort of experiment a bit in terms of getting the concentrations right. I also used a particular kind of milk that I'm going to explain in a minute why it might also help. But that's what I got in terms of the blue scattering as it comes in from the side. And if you illuminate it from the back, it's orange. Okay, so now those of you who are trying it at home, I'd love you to either put in the chat, if you could get it working, let me know, send me an email. It'd be great to know if this does actually, this is the first time, it was only over the summer that I discovered somebody explaining this to say, look, milk is a Rayleigh scatterer. So I did some experiments on this because at first I didn't believe it. And so it's definitely, oh, somebody's in the chat. Oh, Kerry says, excellent. So there you go. It's not just me making it up, all right? And I've not adjusted these pictures to try to make them look more extreme. Now, what I want to explain to you is why, on the one hand, I'm saying milk is an optical scatterer because it's got large blobs of fat in it, and that's why it's white. But at the same time, I'm trying to, it's a Rayleigh scatter. So I did some research over the summer about what actually constitutes milk. And what I found was that, oops, wrong way. What I find is that milk is composed, it's not just fat blobs that are suspended in the water. There's also these things that are called casein micelles. And the casein micelles are very much smaller. They're 2 or 3 orders of magnitude smaller than the fat blobs. And that's where the protein resides. Okay, so the interesting thing about the casein micelles, that's what allows you to make cheese, because as these protein, these much smaller blobs of protein actually combine together, that's what gives a solidity to cheese as you drain out the water, and so you end up with fat, but you also end up with the protein of the casein micelles, and they have particular qualities that allow them to coagulate together to make solids. But with a bit of research, what I think is happening, I'm fairly confident it is happening, is that when you have lots of milk, fat blobs are the things that dominate, and they are optical scatterers, and they scatter all the wavelengths equally. When you thin it out significantly, then you do end up with the fat blobs, but the droplets of fat, because they scatter the light equally in all directions, they don't add any color. They don't add anything interesting in terms of the scattering. They're just scattering all the wavelengths. But the casein micelles then dominate because there's not so many of the droplets of fat to dominate all the scattering. And these smaller Rayleigh scatterers actually start to exhibit some Rayleigh scattering. And certainly my experiments, some of you might be thinking ahead here, is that, well, how do you increase the proportion of casein micelles and reduce the proportion of the fat droplets? Well, one way to do it is to go to less fatty milk, so going to skimmed milk. And so the photographs that I showed you were using skimmed milk, and skimmed milk has removed much of the fat, but it leaves these casein micelles. And if you look at the difference between full fat milk and skimmed milk, you will see that skimmed milk looks a lot thinner. It's not quite so opaquely white because you've got rid of these nice big optical scatterers. But because it leaves the casein micelle scatterers, then you get much more of the Rayleigh scattering effect. So if you want to try this at home, so Pan has just said, use skimmed milk. Oh, and some Akinori has also tried it, and it looks blue. Perfect. And should it look orange if you look from the light from behind? Okay, so a very low concentration, but the skimmed milk I think works a bit better because you've got less fat, but so you've got proportionally more of the Rayleigh scatterers. Okay, so this is fantastic because if you do that experiment with, oops, that's not what I meant to do. If you do that experiment with milk, what you're doing is actually experimenting with this graph. Okay, so this graph ceases to become something just abstract and confusing, but the shape of this graph can be explained by those milk experiments. So a full glass of milk is very much into the optical region, dominated by these large droplets of fat that are optical scatterers. No color effect because they scatter equally, all the wavelengths equally. The smaller casein micelles, though, if you can get the concentration just right, they dominate the scattering, and they've got such a steep slope here, is that the orangey red light gets through because there's no scattering, and the bluer light is scattered. So if you look at the side, you get that bluish effect. If you look from behind, it looks orange, and that's what that's what that experiment is trying to show there. So go away. You know, you're all stuck at home anyway with looking for things to do. There's some experiments that you can all do at home. And if you don't have any milk, go and get skimmed milk, because that's going to likely work better. How does this apply to us measuring the atmosphere? Well, if we look at the size distribution of those, some of the aerosols that we mentioned. So the atmospheric gas molecule down here in nanometers of size, and that's why the sky looks blue. Many of our aerosols that we had on that list cover this range here. So looking in the ultraviolet, the visible, and the near infrared, we can look at the scattering effects from the atmosphere to determine the size and density and number density of the scattering objects. And then liquid hydrometeors, they become, that's clouds, so droplets in fog. Smaller ones are in fog, larger ones are in big clouds, or into lumps of ice. And that's where we get into the microwave domain, and they're very good for measuring. That's why you use radar systems for measuring rain. And it has been a tropical rainfall mapping mission. The TRIM mission was one of the first key successful missions that used a rain radar to actually pick up these particles in the atmosphere using microwave signals. Oh, and that was just a little graphic to emphasize the fact that all these aerosols in the atmosphere range in size quite considerably. So by many orders of magnitudes, to fractions of a micron to many hundreds of microns. And so the scattering effect for each of the different types of aerosols can be observed if you look across different wavelengths of scattering. Right, the final thing to consider here is our the conditions under which we're going to make these measurements. Just getting the pen set up. So our first option here is what's called nadir sounding. We're going to look at its sounding, and so therefore we're looking at emission from the atmosphere. The nadir is the point directly below the satellite. Here's our satellites here. And so the nadir sounding looks directly down towards the surface, and it looks through the atmosphere. And what we're trying to look at here is the emission that comes from the atmosphere. The one particular problem that we have in this context is that we've got signals that come from not just the atmosphere, but also emission that's coming from the Earth's surface, from behind the atmosphere. So that's something that we have to take into account. When we look straight down at nadir, though, one of the problems that we're going to have is that the high altitude layers, or into the middle and upper atmosphere, is that the density of the gas in the middle and upper atmosphere is so low that the signal that we're going to get when we look straight down is insignificant coming from the upper atmosphere compared to deep down in the troposphere, because there's so much gas there. So it's really difficult to measure gases in the upper atmosphere if we look straight down. The alternative to that is to do what's called limb sounding. So limb comes from the lattice limbus, meaning the edge or the border. And this way, what we're doing is looking so that we'd have dark space as the background. It's not completely zero. It's got a black body radiation equivalent to 3.1 Kelvin, but it's very consistent. It's not like the Earth's surface that varies quite a lot. It's very consistent at 3.1 Kelvin. and we get, so we've got a nice background there. And what we can do is scan down through the atmosphere and look at these different layers and look at the emission that's coming from the atmosphere. And one of the key advantages here is that we have the lowest layer that you're looking at is that as you look through here, the lowest layer that you're looking at has a very long path length through the atmosphere. The higher, you get no signal from deeper in the atmosphere, and you only get a little bit of signal. See how the path length through the atmosphere is much less for the higher layers, and it's only the tangent layer that has a very long path. So very low concentrations of gases, we're actually getting to look at quite a lot of it. It means you have a very large horizontal spatial resolution, but you get a much better and finer detail in the vertical resolution, and you can pick up very, very small concentrations of gases using the limb sounding technique. And this is just a little animation showing you that as your satellite orbits, you essentially just keep looking at the limb. So you've never got Earth as the background. You've always got deep space as the background. It's not to scale, obviously, but you're able to get many measurements around the globe, and many of the measurements of the upper atmosphere are done using limb sounding techniques. So this was just saying in terms of looking at the emission, the problem is you've got the background of the Earth through the atmosphere, and it's variable. So the land surface has lots of different, has variation in the signal that's being emitted. The ocean surface also has variation. And the other challenge is how do you actually see it in the atmosphere? Now, if we plot, roughly speaking, what the pressure of the atmosphere looks like, it's an exponential drop off. So pressure drops off very quickly. Now, this is in our advantage here, because what we find is that if we look at a particular wavelength, so if we look at one specific wavelength that is not quite fully transparent, but not quite fully opaque, so it's not quite a wall or window, it's somewhere in between that atmospheric wall and atmospheric window, is that we do see down through to the Earth's surface. So we get some signal that comes from the Earth's surface that will reach our satellite at the top. But even though there's a lot of energy coming from the background, a lot of it gets absorbed. So in terms of the total amount of energy that we actually see from the background, it might not be very significant because it's got lots of atmosphere to get through. And so a lot of that energy gets absorbed on the way. At the high altitude, we might not get much signal simply because the density is so low that even if it has high concentrations of the gas you're looking at, there's just not enough molecules to generate a very large signal. So somewhere in between, the atmosphere is emitting radiation, and the atmosphere above it is very thin, so all that radiation gets through. But the atmosphere is thick enough to stop the radiation getting to you from deeper down. So much of the radiation actually ends up coming from some section of the atmosphere, and you have what is called a sensitivity function, or a weighting function, that looks kind of like this. So radiation from deep down in the atmosphere you don't see because it gets absorbed before it reaches you, and radiation high up in the atmosphere doesn't have much of a signal. There's no sensitivity there because there's so little atmosphere. So most of your sensitivity actually ends up at one particular altitude. And these weighting functions are very sensitive to the wavelength you choose. If you choose a wavelength that is very close to being an atmospheric wind, then your weighting function might look like this, where most of the signal coming from the ground surface actually gets through, and some of it from deeper down in the atmosphere. If you look at another signal which is very near an atmospheric wall, so most of the atmosphere absorbing all of the radiation that you're looking at, your weighting function might look something more like that. because you're looking at a wavelength which is very opaque in the atmosphere. So all the deeper radiation doesn't reach you. All the higher radiation isn't intense enough. So you get a peak here. And by choosing, if you're looking straight down at the nadir, by choosing a set of well-chosen wavelengths, you actually end up with these patterns. So these are from particular microwave sounders looking at all the different bands that they measure. So this particular microwave sounder, for example, is measuring 16 different wavelengths or frequencies. And each one of those has a sensitivity function that looks like this. So down to these blue lines down here, they're almost like atmospheric windows. And the ones up here are much more like atmospheric walls because you can't see down to the surface. And by choosing a good collection of these wavelengths, you can then vary your sensitivity with altitude and derive vertical profile information of the thing that you're trying to measure. You actually use these signals down here. These ones that get right down in the deep blue are mostly getting a signal coming from the Earth's surface. But that's quite handy because you can actually use that to measure what the background signal is to help interpret and improve the quality of all your other measurements. So two more setups in terms of measuring the atmosphere. This one is called occultation. So occultation is based on the absorption. Oops. So this term occultation, it has the same origin as the word occult. So the word occult is usually used to refer to things to do with sort of magic and the dark arts. But the origin of the word is that it comes from, I think it's the Latin that means hidden. So it's to do with hidden knowledge is where the occult comes from. But in this context, occultation is to do with our source over here, one of these sources over on this side, being hidden by the atmosphere. So as it gets hidden by the atmosphere, we're going to make measurements. So our satellite over here will first of all measure our target, and it could be this, it could be a star, or it could be our radio source. But it means that we get a clear view, first of all, of what the source looks like. And then as we look further down in the atmosphere, so in this case here, the sun is essentially setting behind the atmosphere. And as it sets, we'll start to see all the absorption taking place in the atmosphere that's based on the chemical constituents of what's in the atmosphere that we're looking at. It again has the advantage that the long path length on the tangent layer means that we get very good sensitivity in the vertical direction, although the horizontal resolution is much poorer. The key difference between occultation and the sounding is the occultation is measuring the absorption. So you need this extra source behind. The key advantage of a star, there's two advantages of using stars for stellar occultation. One is that they're very small. So it means that you get a nice point of light to look as it goes down and sets through the atmosphere. The other thing is that if I show this next diagram, this little animation, so this animation shows you that you don't get as many measurements as limb sounding because you only get a measurement when you're looking at your source. So here, satellites that use stellar occultation, not solar occultation, what you've got is a sunset and then a sunrise. So the sun, you're watching the sun go down and then through the atmosphere and then rise through the atmosphere. So you'll get two measurements on every orbit, a sunrise and a sunset. Limb sounding is sounding all the time. But if you have multiple stars that are around here, you can collect many more measurements because you've only got one sun, but you've got multiple stars that you could use. And then the last setup is the scattering. So what you use for measuring scattering is you have the sun as your source. The sunlight comes in, and then it scatters off the particles in the atmosphere. And typically what you're using the scattering for is that you're trying to measure aerosols. So you're measuring actual solid particles in the atmosphere. That is essentially what you're doing when you're looking at clouds. So when you're looking at clouds, you're seeing the scattering off the large droplets of water. Again, you're dependent on the sunlight, so you need to make sure that your orbit is aligned so that you're getting scattering from the sun. And this diagram, this is very busy. This is just to show you, I'm going to give you a PDF of this diagram. This pretty much summarizes, or the diagram that you're going to get will summarize everything that I've covered today. So pretty much all the key points are in this diagram. And I'll upload that as a PDF as soon as I've finished. Oh, and somebody's asking, Ewan is asking if it would work with non-cow milk, soya, almond, etc. The answer to that is, I don't know. So I would love for you, Ewan, to do that experiment and let me know. And the my guess is that it will work. Oh, Kerry's saying it appeared to work with oat milk. So what I don't know is what those milks are composed of. They definitely have large enough particles to act as optical scatterers because they look white. So that's a telltale sign that that it's not a liquid, it's not a dissolved liquid. It's actually a suspension of some solid particle in there, and there'll be droplets of probably fat or oil that are that's causing that. What I don't know is if any of those milks will have the equivalent of the casein micelles that are very much smaller particles that will actually give you the Rayleigh scatter. Although Kerry seems to think that it did work. There was another question there, which is, would you please explain what is the sphere divided by pi a squared, the y-axis? So that's what's called the scattering cross-section. So I'm not going to go into the details of the scattering cross-section other than to say that the scattering cross-section is a measure of how well it scatters. And so does it scatter as you would expect it to do with a physical size? If it's got a physical size of pi r squared, does it scatter as much as a pi r squared object should scatter? And that sounds like a strange question, except for the fact that when you get into Rayleigh scattering, it is quite unusual in that it doesn't scatter as much as the size of the object would suggest. It actually drops off much faster than so the object is still getting smaller, but the scattering is actually dropping off much faster than that. And yeah, I will have a think about whether or not there's a better way to show that. But you have to look up what's called the scattering cross-section to understand fully what's going on there. Right, there's one final postscript and then I'm going to end. And the postscript is that a lot of what we've been talking about relates to what's called the Earth radiation. And the Earth radiation budget is the study of looking at how much energy comes and goes from planet Earth. Now, the key thing about a body like Earth suspended in space is that the only way, apart from a very tiny, tiny amount of energy that comes from the core, so the geothermal energy, but let's put that to one side just now, is that the only way that the planet Earth gets energy is by arriving electromagnetic radiation from the sun. And the only way that it can lose energy is by either reflecting or scattering that energy back, or by emitting longer wavelength thermal radiation. And this is one of the key driving forces in terms of whether or not the Earth is getting warmer or cooler. If we are not losing as much energy as is arriving, so if more energy comes in than goes out, where does that energy go? And that energy is going to find its way to being temperature, and it's going to be stored in the Earth system somewhere. And typically that's going to raise the temperature. What will happen though is that the planet will eventually increase in temperature enough that what you should know from black body radiation is that if you increase the temperature, it emits more radiation. So eventually the planet will increase by enough temperature that it will emit enough radiation again to balance out. So you have 100% coming in and 100% going out. Small changes in that have a potential big impact on what the climate is doing on Earth. It's one of the key things that you can only really do this from space. So satellite remote sensing is key in terms of studying the Earth radiation budget, because it means you can get outside of the Earth system. You can measure how much radiation is arriving from the sun. You can measure how much radiation is leaving the planet. it's actually a very complicated and difficult task to do. But one of the key things in here, all the surface stuff that you will be studying has a role in there, but also measuring the atmosphere, because the atmosphere is one of the key drivers of how much energy is coming and going. The clouds in the atmosphere and the aerosols contribute a significant amount of this balance, so about a third of it, because it scatters that energy straight back out into space. It never warms up the planet. But the emitted radiation from the Earth's surface interacts with the atmosphere, and in the thermal infrared zone, the atmosphere does have absorption lines. So chemical constituents in the atmosphere actually absorb radiation, and it also emits radiation. And so this balance in here is driven very much by the chemical and physical state of the atmosphere. And remote sensing from satellites can significantly contribute to the science of understanding what's happening in the process. So to take our diagram and put it into the context of a climate change discussion, is that essentially what we've been looking at here is that the absorption of the Earth's atmosphere is driven by all these constituents that are within the atmosphere. Plus, if you remember, when you look in detail, you'll find that there's lots more. Almost all of the gases in the atmosphere will have absorption lines somewhere. Now, the key thing in this diagram is that what you have is that the black body radiation curve, the Planck radiation curve, which you were introduced to last week, I think, is that an object with a physical temperature emits radiation. As that temperature warms up, the peak goes to shorter and shorter wavelengths, so higher frequency, and the total amount of energy, so the area under the curve here, also goes up. Now, it's not coincidence, it's just evolution that your eyes are sensitive to the peak part of the solar output. So the solar, the sun, surface of the sun is about 6,000 Kelvin. So the peak in the black body radiation is in what we call the visible part of the spectrum. And it makes sense for us to have evolved eyes sensitive to that part, because not only is that where most of the radiation is coming from the sun, but it's also in the zone where it's relatively transparent. So it's in the atmospheric windows. So the radiation from the sun comes in through that window and warms up the planet's surface. The planet warms up to something around 300 Kelvin and then tries to emit that radiation, because it has to get rid of that energy somehow. It can't just keep storing it. And it happens to emit that radiation into the thermal infrared, going into the microwave zone. And that's quite significant, so that these atmospheric walls and these individual lines that are absorbing, that have absorption lines, is what drives what is referred to as the greenhouse effect. We can have a long discussion about whether or not it's the right name or not, but it's called the greenhouse effect, because these gases in the atmosphere have absorption lines that are within the emission of the Earth's surface at 300 Kelvin. So the context in which what we've been talking about and measurements of the atmosphere and how radiation interacts with the atmosphere is also what is driving our understanding of climate change. So that if you look at this diagram, is that if some of these absorption lines, if you increase the concentration of some of these gases, CO2, methane, as you increase the concentration of these gases, their absorption lines get larger. And if they get larger, then they are actually absorbing more of that energy that the Earth is trying to lose by emitting it at 300 Kelvin. So you start to fill in these gaps. More of that energy is absorbed by the atmosphere. And in order for the atmosphere to get rid of that energy, the atmosphere has to warm up so that the top of the atmosphere can actually emit more radiation and bring back into balance the Earth radiation budget. So you've got the same coming in as going out. Right, there was a couple of questions I will answer. So that's where I'm going to finish. That was your feed in to say that, well, if you're going to measure the atmosphere with Earth observation and remote sensing, then understanding the properties. Oh, I forgot to put my lights back on. understanding the properties of electromagnetic radiation and the atmosphere, they're all tied together with topics to do with studying the Earth system and climate change. Right, I'll answer. What was the question that came up? What vertical resolution can you get with limb sounding, occultation, and what resolution is useful in general? So the vertical resolution of limb sounding is on the region of, I think it's sort of 2 or 3 kilometers in altitude. I think up to about 5 kilometers. It's about 20 kilometers when you're doing nadir sounding. So if you're looking straight down and trying to use those weighting functions, you're generally certainly about 10 times worse vertical resolution. But if you're looking at nadir, you get all the benefit of the instantaneous field of view. So you can get maybe 25 kilometers in horizontal resolution looking straight down, but you're whereas in limb sounding or occultation, you're at about 150 kilometers in terms of your horizontal resolution.